Okay, so we'll move on to the next topic. So in the last class, we were looking at shift reduce parsers, and we saw that at certain situations there is a conflict or there is an ambiguity about whether the parser should do a shift or a reduce. There is a shift reduce conflict and reduce conflict, which we saw, right? So the what action to take is ambiguous in such situations. The next class of parsers or next what we are going to look at is how to bring determinism into parsing. Okay, different techniques for bringing determinism into parsing. Determinism means you want to actually have, there should not be any ambiguity. That is what determinism is. So how can we do that? Now, first method which we are going to discuss is actually some sort of heuristic method. It is not actually an algorithm, but we are looking at how humans do parsing in our mind. That is, when we are talking or when we read a sentence, there might be ambiguities which arise. So when you're listening to someone talk, there might be, we are not actually looking at the sentence and we look at the different parse trees which can be generated or the different of the different methods in which the parse trees can be generated, different methods that the sentence can be interpreted. Okay, we are not looking at that, but instead, generally how humans process is we look at it incrementally, like we do in a greedy algorithm. So at this point, what is the best option? So how can we process it in an unambiguous way? So we will look at some of the techniques that humans use in order to parse in a deterministic fashion, and those are some heuristic rules which can be applied to a shift reduce parser in order to resolve conflicts. Okay, so here, okay, human parsing seems close to a deterministic process. That is a process that doesn't search alternatives, but rather uses the information it has at a particular point in time to choose the correct interpretation. That is what humans do. And how do humans do this? Okay, one principle which intuitively that humans apply is called the minimal attachment principle, where the preference is given for syntactic analysis that creates the least number of nodes in a parse tree. It is not intentionally done by the human, but this is what the human does intuitively. Okay, so the principle is the humans actually give preference to a syntax analysis in which the number of nodes created in the parse tree is minimal, a number of nodes or the number of non-terminals which are generated. Say, for example, the man kept the dog in the house. Okay, so this is a sentence. So you can say the man kept the dog in the house. That is, the man is keeping a particular dog in the house. Or you can interpret it as the man kept the dog in the house. Okay, so the dog in the house is actually a noun phrase. So the in the house is actually here attaching to the dog, or it is describing the dog. So the man is keeping the dog in the house. But in this case, the man kept the dog in the house. So uh, the man is keeping the dog inside his house and not he is keeping the dog in the house. Okay, these are two interpretations. So we would generally prefer this, right? As humans, we would prefer the man kept the dog in the house. That is, man is keeping the dog inside the house. That is the interpretation which humans generally prefer. And if you look at this tree, the number of non-terminals which is generated is 1, 2, 3, 4, 5, 6 here in the first interpretation. Second one is 1, 2, 3, 4, 5, 6, 7. The number of nodes generated here is lesser. Okay, so this is the interpretation which is chosen by human, and that principle is called the minimal attachment principle. So this is one heuristic which we can apply in order to do a disambiguation of a particular parse. Okay, now another principle is called the right association principle. So what it says is all other things being equal, the new constituents tend to be interpreted as being part of the current constituent under construction rather than part of some constituent higher on the parse stack. Okay, so instead of that is when you're reading from left to right, if you come across, say, first you come across the subject of a sentence, then you come across a verb, and after that you come across maybe an object in which you can have a noun phrase followed by prepositional phrase, and so on. Multiple things can be attached together. Okay, so what we tend to do is we tend to attach, as we go on, we tend to attach something to uh, uh, the constituent which is closer to it than to a higher level entity. That is what right association is saying. And if you look at this example, George said that Henry left in his car. Okay, so what George said is, one interpretation is, what George said is that Henry left in his car. In his means Henry's car, right? So that is one interpretation. Another interpretation is George said that Henry left. And where did he say it? While he was in his car, he said that. Okay, so these are two interpretations. Both of them are syntactically acceptable. So first interpretation is Henry left in the car. That is the interpretation. Second one is George spoke that Henry left. That is, he spoke it while he was in the car. That is the second interpretation. And uh, in right association, okay, in first case, it attaches the prepositional phrase in his car is attached to the verb phrase immediately preceding. That is, in his car, here, in his car is a prepositional phrase. That is a preposition follow, and you have a phrase attached to it. And in first one, it attaches a preposition to the verb phrase immediately preceding that. In his car is attached to left. So Henry left in his car. In the case of second interpretation, it is attached the verb phrase higher up in the stack or higher up in the parse tree. Okay, that is said like attached here. Okay, so what humans generally do is, or what right association principle says is, you attach a particular constituent to the one which is closer to it. So this is the interpretation which we generally choose. Here we have got two interpretations. We choose the one with right association. That is humans. That is how humans interpret sentence. Okay. Then another way of disambiguation is based on lexical preferences. So lexical preferences, what we mean is verbs, the verb which we use can actually affect the way we make attachments. Okay, so I wanted the dog in the house. So here again there is an ambiguity. I wanted the dog. Where do you want the dog to be kept? In the house. Okay, or I can say I wanted the dog in the house. That is, I went to a place and I saw a dog and I wanted that dog in the house. Okay, that is another interpretation. So here we have got an ambiguity. But if you look at, let us say, this sentence 3, I put the dog in the house. So I put the dog in the house. So in the house is the prepositional phrase. It always attaches to put only, right? You can only put the dog somewhere. So this in the house can attach to this. You cannot say I put the dog in the house. You cannot say that. So based on what sort of verb you are using, or based on verb is one example. So based on that particular lexical entity, the attachments might prefer. So that is another method for disambiguation. Okay. So these are three different methods of disambiguation which can be used as heuristic rules in order to what try to decide on which of the ambiguous parse trees can be considered at a time. Okay, so this is one way of doing it. Okay, so one recent suggestion following the first approach is that human preferences in parsing could be used to choose the rule. So the approaches are: right association strategy corresponds to favoring shift of operations over reduce operations. So if you have a shift reduce conflict, what right association says is, whatever is there on the right, it attaches to the statement which is or the constituent which is closest to it, which means you always prefer to shift operations onto the stack, and then you consider it as a unit. Okay, so according to right association strategy, you will prefer shift operations over reduce operations when you have a shift reduce conflict. Now, if you have a minimal attachment strategy, if you're using a minimal attachment strategy, and if you have a reduce conflict, it favors the minimal attachment strategy favors the longest road. Uh, Basically, in minimal attachment strategy, what we said is uh, this is right. We prefer less number of non-terminal symbols. So if you want non-terminal symbols to be less, then what you do is you try to reduce the number of if you want to reduce the number of non-terminals, then കൂടുതൽ number of that is more number of എന്താണ് this can be combined. Okay, more number of words can be combined into a particular non-terminal, or more number of lexical entities can be combined into a non-terminal. Okay, so which means that is how you can reduce the number of non-terminals. So minimal attachment principles actually prefer to have what more number of it prefers the longest rule, or you want to have more number of symbols on the stack to be combined in order to reduce to a non-phrase. So if you have a reduce conflict, okay, if you have a reduce conflict, and say we have one say noun phrase gives say an adjective followed by a noun phrase, and another is simply a noun phrase gives a noun. So the longest root principle is you prefer the longer value, the production with the longer value on the right hand side. So when you have a conflict like this, so that is what minimal attachment strategy is saying. Okay, so this is heuristic based determinism. Okay, now next we will look at the concept of look ahead. This is another way to uh, what make the parser deterministic or remove ambiguity. Right. So look ahead. I think you must have come across look ahead in case of LR parsers, LALR parsers, and so on. How if you are look ahead means the idea is you want to look at the look ahead at the input symbol, one more value or two more values. If you are able to look ahead into the input symbols, then we will be able to decide which of the productions we can apply. That is a concept of look ahead, right? So you can the can be resolved more effectively. The parser is allowed to inspect words further down by down the input stream, or that is the concept of look ahead. Generally, a look ahead of one or two only is allowed, because otherwise what happens is the sort of when you design a parser, we said we start with the transition diagram, right? The transition diagram becomes uh, the number of states in that diagram becomes extremely large. When the number of look ahead symbols increase, it exponentially increases. So generally we only go for one or two look ahead symbols. And a look ahead is generally specified like this. That is, here if you have three symbols, so what it means is here you have got a noun on the top of the stack, and then in the input look ahead symbols are these. You are expecting either an auxiliary verb and followed by an actual verb in the infinite form. So in that case you apply some rule and so on. Okay, so this is how look ahead works. So that is a general idea of look ahead. And now what we are going to look at is called a Marcus parser, which is actually a deterministic parser, which was proposed by Marcus somewhere in the 1970s, actually, for natural language processing. So we'll generally have an idea of what this Marcus parser is and how it introduces determinism in parsing. Okay. So in Marcus Parser, what it does is instead of shift and reduce operations, it allows more actions. Okay, rather than shift reduce operations, the parser builds constituents. The principle is the parser build constituents incrementally by attaching buffer elements into their parent constituent. Okay, like in the case of register assignment. Remember, we talked about registers in the case of augmented grammars or augmented transition networks. If you remember, what we did is we attach features or registers onto each of the constituents. This is the parsing here is done something similar to that. And here, rather than shifting a noun phrase onto a stack, what it does is it creates an S constituent on the parts and attaches the NP to the stack. Okay. So generally what we do is when we come across this, we push NP onto the stack and so on. But here what we do is for the S constituent, S stands for a sentence, right? For the sentence, we create something like a feature called NP. What is a noun phrase attached to this particular sentence, and you attach a value to it. Okay, so that is how parsing is done. This is not a look ahead part, but in markers parser, how it builds. Okay, how it builds the constituents of the parse. That is what we are talking about here. Look ahead part is based on some set of look ahead rules, which we will look at later. Okay, and here there is no reduce operation. So what are the operations involved in Marcus parser? So what is Marcus parser? It is basically a deterministic parser for natural languages, and it does the parsing by building constituents incrementally and associates registers to the different constituents. Okay, and it also has a look ahead part which involves a set of look ahead rules. Okay. So the main operations associated with the Marcus parser is it can create a new node on the parse stack. That is one operation allowed, and it can attach an input constituent to the top node of the parse stack. Okay. Say input constituent, like we said earlier, might be a noun phrase. A noun phrase can be attached to whatever is there on the top of the stack. If it is a sentence, S is there on the top of the stack, then you can attach the noun phrase as a feature to this top of the stack. Okay, and drop node in the part stack. Drop. So this create node on the stack is similar to pushing onto the stack, and drop is actually popping symbols from the stack and putting it back to the buffer. Okay, so again it is like shift reduce parser itself. You have got a stack as well as the buffer. Okay, and create node is equivalent to pushing elements onto the parse stack, and dropping is to pop it and place it on to the input buffer. Okay, and then you another operation you have is attaching an input constituent to the top node of the parse stack. Now we look at examples here. So this is only, we are not looking at the continuous parsing. So given a sentence like this, after okay, initially we will have S, right? Then we will go for the applying the productions and so on. And this is this state actually reflects after the cat look on the buffer you had the cat ate the fish, so the cat has been parsed. Okay, so in that case what will be the state of the stack? That is what is shown. So top of the stack you have, so this noun phrase has already been parsed, and corresponding to the noun phrase you have got features or registers with values. The determinant of this noun phrase is the, and the head of the noun phrase is cat. So this information was attached earlier, and this whole noun phrase is another register which is or a feature which is attached to the the subject feature of sentence. So the subject of the sentence is noun phrase, and the noun phrase consists of a determinant followed by a noun, which is the head of the noun phrase. Okay, head is the most important part of the noun phrase. Okay, so this is the state of the stack after the cat has been processed. Now we will look at the next input onto the stack. We are just looking at what are the operations which are possible. How look ahead is done, we'll look at later. Okay, now given we have a verb. So how do you process this verb? So based on the productions we have, we know this ate is actually uh, uh, a verb, right? And what is done here is, now the verb has been processed and it is attached to the main verb feature of the sentence. So subject is a feature of the feature or a register of the sentence. Similarly, main verb is also a feature of the sentence. So the main verb of the sentence is ate. That has been done. And now what is done? You have pushed another noun phrase onto the stack. So this is the noun phrase is the top of the stack. This constituent is below the top of the stack. Now what do? You come across the, so you have got a reduction to a determiner, and that determinant can be attached as a determinant feature to NP. And similarly, which is the head part of the noun phrase, it can be attached to the noun phrase head feature and so on. So those are actions which will be there as part of the rules, the look ahead rules. Okay. So this is just to illustrate how or what are the operations which happen in the case of the Markov parser. Okay, so this is a state after NP has been created. Now another important thing to understand is the concept of a packet. Okay, a packet consists of a set of look ahead rules. Okay, so the rules actually identify the appropriate parser action to a given situation, and at the same time additional actions are available for changing the parse state. Okay, so we have a set of look ahead symbols which identify the appropriate action for a given situation and also for changing the state of the parser. Okay, and the actions can be either to attach constituents like we saw earlier, or you can say activate a packet and deactivate a packet. So packet means, we said, is a set of rules. We look at an example. Okay, this is a packet. Look, this is a packet with a particular name. Build ox is the name of the packet, and it has a set of rules like this. So what this rule says is, look, if you have in the look ahead symbol, if you have an auxiliary called have, and the form of the auxiliary verb is a normal verb form, okay, or it is an auxiliary form be and the form is an ing form. So what is the action to be taken? So this is how you give the rules, look ahead rules. So these 1 2 3 4 5 etc are the look ahead rules associated with a particular packet. And look, this is the action, attach what, this is perfect tense. Okay, that is a feature. So you have to append the tense of the verb here, and here you have got a priority associated with it. So the priority is, since there are multiple rules, you might have to give preferences certain rules over the other. Say for example, this is a rule which is true always. Okay, so when none of these rules are applicable, only we need to apply this rule. So in order to do that, we give least priority. 15 is a larger number, it has a lower priority. So when none of these rules are applicable, you can give this particular lower priority to that particular rule. Okay, and each of these packets are actually associated with a symbol. Okay, so built ox packet is associated with the auxiliary verb. Similarly, we can associate packets with other constituents also. Okay, so how parsing is done is, uh, in the case of Markerparser, it is a combination of look ahead as well as augmented transition networks. Okay, so in augmented transition networks, we saw that we can associate features with each of the symbols, right? Each of the symbols. So at the end of the parse, S will contain all the associated features which you will attach from the lower ends of the tree. And along with that, that is along with the augmentation feature, here we also associate what are known as packets containing look-ahead rules in order to bring about some disambiguation to the rules also. So in short, Marker's parser is a deterministic parser, which is maybe a combination of augmented transition networks and look-ahead rules. So combination of the two in order to do parsing. This is what this Marker's parser is. Okay.